Hello everyone, and welcome to some more remote learning. In this video, we're going to go over volume by shells. So we're still doing that solid revolution, but now as opposed to creating those disk slices, we're going to actually create cylinders or shells. So let's take a look at how that solid is formed. In this graph on the left-hand side of my page, I have two separate functions. I have the blue line is y equals 4x, and the red line is y equals x cubed. We're going to talk about revolving this around the y-axis. So if you remember from doing the disk method, if I told you to revolve this around the y-axis, we would want to draw those rectangles horizontally so that when we revolved it around that axis, we would get those flat disks or washers. But since now we're doing the shell method, even though we're revolving around that y-axis, we want to draw our rectangles vertically because you can see when that's revolved around, that's going to be a cylinder. So if this is our region, I'll shade it in yellow, we would draw our rectangles so that we're integrating with respect to x. You see that little width is a change in x, a dx. So drawing those rectangles vertically, rotating them around, you can see that that's going to form a shell. So some hollow cylinder when that's revolved around. But that's just a piece of our overall volume. We're going to do that going all the way, filling in everything with rectangles, revolving all of them around. And remember, volume is when we integrate the area. But what is this area? With disk and washer, it was easy to tell the area because it's all based on pi r squared. But this area, when you see that I take that rectangle and revolve it around, like I said before, I'm going to have that hollow cylinder. So let's redraw this hollow cylinder up here. So you can see that this little length here would have been that dx. But let's envision actually cutting this open and unrolling that shell or unrolling that cylinder. So if I split this and rolled it out, we would get a rectangle. But we would actually get a rectangular prism because remember we have that width dx. So here would be our width of dx, the change in x. The next thing we need to figure out is what is this length here? That is the height. The height of our cylinder is this length from one function to the other function. So noting back to the region between curves, that's going to be one function minus our other function, our top function minus our bottom function. That's the height. And one more thing to figure out in order to build the volume is this length here, which we took this and unrolled it from the cylinder. So that length here, which I just highlighted in yellow, is the circumference of a cylinder, or the circumference of this circle. And what's that circumference? That circumference formula is 2 pi r, where r is our radius, and that's the distance from the line we revolve around. So overall, for using the shell method, volume is going to be from some bounds, I'll just say A to B, and we need our shell circumference times our shell height. And that all gets integrated with respect to either x or either y, depending on which way those rectangles are drawn. So let's move on to this blue box and fill in just a general formula. So the shell method about the y-axis, we're going to need to draw our rectangles vertically. So that means we're going to be integrating with respect to x when revolving around a y-axis or anything parallel to that. So our volume V is going to be equal to some bounds from A to B, which is where we start drawing our rectangles and where we stop drawing our rectangles. Then my shell circumference is 2 pi times r. But what exactly is r? Well, in the case of revolving around an axis, r is that distance to our rectangle from the axis. So looking up above, let me go ahead and zoom in, r is going to be this distance here. But what is that distance? Well, that distance is whatever x value we're at. So this is just x. So our radius, r, is really x. So there we have our shell circumference. Now we just need to do our shell height, which is our top function minus our bottom function when integrating with respect to x. So that's going to be some function f of x minus some function g of x, where along the interval from a to b, f of x is going to be greater than or equal to g of x. And this is all integrated with respect to x. Now quickly I want to note that this x right here represents the radius. So, like you'll see in example 2, when we're revolving around something that's not the axis, x is not going to be the radius by itself. It's either going to be x plus some constant or some constant minus x to get that appropriate radius when revolving around something that's not the axis. So just keep that in mind, that that's really the radius. And f of x minus g of x, we know, is that height, and that's where we're either going to do top minus bottom or right minus left, reserving right minus left for when integrating with respect to y. So let's go ahead and continue solving the picture that we did up above. So it said, let r be that region in the first quadrant bounded by y equals x cubed, y equals 4x, and we're going to use the shell method to find the volume of the solid generated when it's revolved around the y-axis. We have a good start for this. We know that volume is going to go from A to B, and then we're going to have the shell circumference times the shell height. So let's first find those intersection points. Well, one intersection point is easy to see and easy to double check. That's going to be this intersection point here, which is 0, 0. And we care about that x value because that's where we're starting to draw those rectangles in the x. So our lower bound is going to be 0, and a quick double check, plugging 0 into either equation is going to give us 0 for y, so they are indeed equal at 0. Next, we need to solve for this top intersection point, the rightmost intersection point where I stop drawing those rectangles. So that's going to be when 4x equals x cubed. So if I was to divide both sides by x, I would get that 4 equals x squared. Taking the square root, that's going to be plus or minus 2 equals x. However, as stated in the problem, we're only dealing with the first quadrant, so that's only going to be my positive 2 value. So this is going to be 2 in the x, and that's where I'll stop drawing my rectangles. Now I don't care about that y value, so I'm not even going to bother solving for what it is. I just know that I'm stopping at 2 in the x for my rectangles. So going from 0 to 2, now we're going to deal with our shell circumference. So that's 2 pi times our radius r. But r, remember, is that distance from our axis, or where we're revolving around, to our rectangle, which you can see when I draw that rectangle, anywhere along that distance is just some x distance. If I drew another rectangle further out, that distance is still whatever my x value is. So my radius is x. So there's my shell circumference. Now I need to do my shell height, which is top minus bottom. You can see that is my height. So my top function is 4x, and my bottom function is x cubed. So this will be 4x minus x cubed. And there we have it. That's going to give me my volume, building those small shells, adding them all together to create my overall solid, starting at 0 and going to 2. So let's go ahead and distribute to make this easier to integrate, and then integrate it. So our volume is going to go from 0 to 2. And what I can do actually is I'm going to pull that 2 pi out in front because that's just some constant that's multiplied to everything, which means all I have to do now is distribute this x to the 4x and the x cubed. So that will be 4x squared minus x to the 4th, all with respect to x. Now I'll integrate. So I'll have 2 pi times 4x squared when integrated is going to be 4x cubed over 3 minus x to the 4th when integrated is going to be x to the 5th over 5. And my bounds for this are from 0 to 2. So when I go to plug in 2, I'll have 2 pi times 4 times 2 cubed is 4 times 8, which is 32, and that's all over 3. And then I have 2 to the 5th, which again is 32, and that's all over 5. Now when I plug in 0, you can see that all of my terms will go away, so I would be subtracting 0 from this function. So all I have is 2 pi times 32 thirds minus 32 fifths, which I'm going to find a common denominator to simplify this down. And between 3 and 5, that common denominator is going to be 15. So I'm going to multiply 32 by 5, and I'm also going to multiply 32 by 3. So I'll have 2 pi times 32 times 5 is 160, so that will be 160 over 15, minus 32 times 3 is 96, so that'll be 96 over 15. 160 minus 96 gives us 64, so that's going to be 2 pi times 64 over 15, and 2 times 64 is 128. So our volume in example 1 is 128 pi over 15. So as we continue on, remember that the volume when doing the shell method is going to be integrating the shell circumference times the shell height. Moving on to example 2, we're going to let R be the region bounded by y equals the square root of x, y equals x over 2, and we're going to use the shell method to find the volume of the solid generated when we're revolved around the line x equals -2. So that's going to be this line over here, x equals -2, that we're revolving around. Our region was between these two curves, which I'll shade in yellow. Now, if we were doing the disk method, we would want our rectangles drawn horizontally so that we get that flat disk when revolved around. However, we're doing the shell method. It says to find the volume using that shell method, so we need to draw our rectangles vertically so that we form those shells to then integrate. So I'll go ahead and draw a few of my rectangles. So the first thing we'll figure out is where we start drawing those rectangles and where we stop drawing those rectangles. And because we're integrating with respect to x, that's that tiny width, then we're going to find those x bounds. So our intersection point is 0, 0, and that upper intersection point is going to be when the square root of x equals x over 2. So the square root of x equals x over 2. If I squared both sides, I'd get that x equals x squared over 4. Multiplying by 4 and then dividing by x on both sides, I would get that 4 equals x. So my intersection point occurs at 4 and the x, and because I'm going to use the same graph later on, let's go ahead and solve for that y value as well. When I plug in 4 for x, I'm going to get 2 for y, because the square root of 4 is 2, or 4 divided by 2 is 2. But I really care about those x coordinate values, so this is going to go from 0 to 4. Now we're going to focus on that shell circumference. So the circumference is 2 pi times r. But this r is the distance from where we're revolving. So the distance between the line we revolve around and where our rectangle is drawn, which is this distance here, or this distance here. How do we find those distances? Well, we know from the axis, from our y-axis to those rectangles, that is some x distance away. Wherever those rectangles are drawn, that is some x. Wherever we are in the x, we'll plug that value in and get the top and bottom of our rectangle, but it's some x. The part that's missing is this part over here on each of those lines that I drew, which we know that distance is how many units away from the axis? 2 units away. That's a distance of 2. So regardless of where our rectangle is at, we know the radius is going to be 2 plus x. So our radius r is 2 plus x. So we have 2 pi times 2 plus x. That is our circumference of that shell. So now our next step is the shell height, top minus bottom, right? So that's going to be the square root of x minus x over 2. That top of that rectangle minus the bottom of that rectangle to get that height. And that's integrated with respect to x. So this is going to be the area of that shell with that width. We're then going to get a volume, and integrating across will give us that entire volume. So now that we have all those pieces, we're ready to solve. I'll pull 2 pi out in front and then simplify this integral down. So I'll distribute 2 plus x with the square root of x minus x over 2 by foiling. So I'll have 2 square root of x first, and then I'm going to subtract 2x over 2, which is going to leave me with x, and then I'll add x times the square root of x, which x to the first times x to the 1/2 is going to be x to the 3/2, and then I'll subtract multiplying x with x over 2, which will be x squared over 2. Now I'll integrate. So I'll have 2 pi times 2 root x when integrated. That x, when adding 1, goes to the 3/2. But then I'll divide by that fraction, which is the same as multiplying by 2/3. So this will be 4/3 x to the 3/2. Then I'll subtract, integrating x becomes x squared over 2, integrating x to the 3/2. So adding 1 to 3/2 will give me 5/2. So this will be x to the 5/2, and when I divide by that fraction, that will be the same as multiplying by 2/5. Now I'll subtract, integrating x squared over 2 would be x cubed over 3 times 2, which is x cubed over 6. And my bounds in the x are from 0 to 4. Now I'll go ahead and plug in that 4 and then subtract, plugging in 0. So I'll have 2 pi times 4 to the 3/2. I'll take the square root first, which will leave me with 2, and then cube it to get 8. 8 times 4 is 32, so I have 32/3 minus 4 squared is 16 over 2. That would be 8, plus, now if I take the square root of 4 again, that would be 2, so I'll have 2 to the 5th, which is 32, but I'm multiplying that by 2, so that's going to be 64 over 5 minus 4 cubed. 4 times 4 is 16. 16 times 4 is 64, so that's 64/6. And the nice thing about 64/6 is that both are divisible by 2. So that's really going to leave me with 32/3. And then when I plug in 0, all of these terms go to 0, so I don't even need to worry about subtracting it. Now from here, you'll see that my 32/3 cancels out with my 32/3. So I'm left with 2 pi times -8 plus 64/5. So if I rewrite this, I'm going to find a common denominator, and that common denominator is 5. So rewriting -8 in terms of fifths, that's going to be -40/5, and I'm adding that to 64/5, which leaves me with 2 pi times 24/5, which, when distributing that 2 pi to that fraction, will be 48 pi over 5. That is the volume of my region revolved around the line x equals -2. Now, if you notice, this figure is not a new figure that we're revolving around the line x equals -2. In that previous worksheet, when we did the disc and washer method, revolved around a line that was not an axis, we did this exact same problem using the disc method. This was practice problem number 3 on that worksheet, and we did indeed get 48 pi over phi. So regardless of the method we use, we're going to get that same volume if we're revolving the same region about the same line. If they specify to use the shell, or if they specify to use the disc washer, use the method that's specified. If they don't, what I recommend is setting it up each way, maybe not doing the whole thing out, but setting it up in your heads, or at least starting it out and seeing which one's easier to integrate, and go with that. And a good double check would be to integrate it using the other method and make sure you get the same thing. But for now, let's move on to example 3. In example 3, we have the region bounded by 2x and 3x minus 1, so that's this region here, when we also include y equals 0. Now it tells us to use the shell method for finding the volume of the solid generated when r is revolved around the x-axis. So now we're revolving around this, and if we're using the shell method, we want our rectangles drawn horizontally so that we get that shell. If we drew them vertically, we'd be getting some disc. And really for this one, if we tried to use the disc method, we would have to split up the integral because our bottom function is different over the course of this region. But if you note, when we draw our rectangles horizontally, then you see that that right function is always the same and the left function is always the same. So this one would definitely be using the shell method. So for this one, even if it didn't specify, I would definitely use the shell method. Now drawing our rectangles like this, we know we're integrating with respect to y. But that same concept of shell circumference times shell height still applies. But let's go back up to our formula box and adjust. If we're revolving about the x-axis, then our volume is going to go, I'll change my bounds to be from some y value c to some y value d, and then we have 2 pi times our radius. But our radius is no longer x. Our radius is still that distance from where we're revolving, except when we're revolving around the x-axis, that distance here is some y value. So even if we drew it up here, that is still some y value away along that entire rectangle. So we'll have 2 pi y for our circumference, and our height is going to be no longer top minus bottom, but right minus left. So some function p of y minus some function q of y. And this is all with respect to y. Again, where this y actually represents our radius. So when we're revolving around something that's not the x-axis, let's say a line like y equals 1, then we're going to have to shift, either adding a constant or taking that constant and subtracting. And then the p of y minus q of y, that is our height. So here we have the right minus left, whereas when integrating with respect to x, we have that top minus bottom, which should be familiar from that region between curves worksheet. So with that being said, we're ready to finish out this example. We know that our volume is going to go from the lower bound to the upper bound in terms of y. So we're starting at y equals 0 as specified, so that's our lower bound, that's where we start drawing those rectangles, but our upper bound occurs at this intersection point here, which is when 2x equals 3x minus 1. So when does 2x equal 3x minus 1? If I subtract 3x, that's negative x equals a negative 1, which means that x equals a positive 1. So my intersection point in terms of x is 1, but I need that y value. So when I plug 1 in to either function, I'll get a y value of 2. So my upper bound for this integral is 2. Now it's just a matter of shell circumference times shell height. So that's 2 pi r, where r we talked about when using that axis is just some distance y. That's my radius r. So 2 pi y times my shell height, that's right minus left. That larger function in terms of y minus that smaller function. That is my height. From here, that blue line to the red line. So my blue line represents 3x minus 1, and then I'm subtracting 2x from that. But wait a second, if I'm integrating with respect to y, do I want x's in here? No. So I'm going to change this to rewrite the functions in terms of y, because my height is really based on what my x value is. It's this x value here minus this x value there. That x value on the right minus that x value on the left, but I get that because it's a function of y. So the blue line, 3x minus 1 equals y, rewriting that in terms of y, that's going to be x equals y plus 1 over 3. So that is my rightmost function in terms of y, and then I'll subtract that leftmost function, right minus left. If y is equal to 2x, that means that x is equal to y over 2. So I'll plug in y over 2 for that leftmost function. Now I'm ready to integrate with respect to y. So again, I'll pull that 2 pi out because it's just some constant that's multiplied to everything. Now, to make this easier on myself, I'll distribute this y to both of my terms. So I'll have y squared over 3 plus y over 3 minus y squared over 2, all with respect to y. And you see, all I did was split this fraction up as y over 3 plus 1 over 3, and that became, when distributing the y squared over 3 plus y over 3. Now quickly, I'm going to simplify this down just a little bit more because I can combine my y squared terms. Y squared over 3 minus y squared over 2, that common denominator is 6. So that's going to be 2y squared over 6 minus 3y squared over 6, which becomes a negative y squared over 6. And I'm adding that to y over 3, and this is with respect to y. Now I'm ready to integrate. So I'll have 2 pi times integrating y squared over 6, that will become y cubed over 18, but it's a negative. So negative y cubed over 18, and then I'm adding that to integrating y over 3, that would be y squared over 6, and my bounds go from 0 to 2. So plugging 2 in for y, I'll get 2 pi times 2 cubed is going to give me 8, so this is negative 8/18, or simplifying, would be negative 4/9, plus 2 squared is 4, so that's 4/6, and then when I plug in 0, I'll be subtracting 0 from this, so I don't need to worry about that. Finding that common denominator, I'll get 2 pi between 9 and 6, that common denominator is 54. But I can see here that because I have two even numbers, I'll take this 4/6 and simplify it down to be 2/3. Then my common denominator is a lot easier to work with. It's just going to be 9. So I'll have negative 4/9 plus, rewriting 2/3 in terms of ninths, that's going to be multiplying both by 3, so 6/9. 2 pi times 2/9 will be my solution, which when simplified will be 4 pi over 9. So 4 pi over 9 is my volume for example 3. Let's continue on to our last example on this worksheet, example number 4. This time we're going to be revolving around another line, but it's going to be parallel to that x-axis, not the x-axis. So our radius is going to be a little different. And like I stated before, I'm going to be using that same region as an example 2. So I know my two intersection points are 0, 0, and 4, 2. because this is the region trapped between the square root of x and x over 2. And in this case, I'm going to be revolving around the line y equals 3. Now, this is the same exact example that I used on that previous worksheet where we did the disk method. We did the disk method revolving around the line y equals 3. And our answer, I'll go ahead and write it out, because when we go to integrate, it'll be a great double check. We should get 16 pi over 3 as our answer. However, when we did the disk method, we drew those rectangles vertically so that we would get flat disks or washers when revolved. Doing the shell method, because it specifies that we need to use the shell method, we're going to be integrating with those rectangles drawn horizontally so that we get a shell, which means we're integrating with respect to y. So our volume is going to equal, well, we need to do our y bounds. We start drawing the rectangle at 0 in the y, and we stop at 2 in the y. So this goes from 0 to 2. Next is our shell circumference. So that's 2 pi times our radius r, where r in this case is the distance from the line we're revolving around. So from the line we're revolving around to the rectangle is this distance here. Now remember, dy is infinitesimally small because we're integrating across that whole entire region. Thinking about the Riemann sums, those rectangles are shrinking down in width. So this distance from here to here, from our axis to our rectangle, plus this distance from our rectangle to our axis, is that entire length. This dy is infinitesimally small, so we don't need to take that into account. But this is helpful for figuring out our radius, because if we do know this distance here, that's like up above in example 3. This distance is some y distance. We're some y above our x-axis. The other distance that I definitely know is this distance here. That full length is 3, because that line is 3 above our axis. So if that distance is 3, and I know that this distance is y, I'm going to be able to solve for r, because that's what I want to know. And r is that total distance of 3 minus the distance of y. So our radius in this case is 3 minus y. So 2 pi times 3 minus y gives us that shell circumference. All we need now is the shell height, which is right minus left, and we want those functions in terms of what variable? In terms of y, because we're integrating with respect to y. So the blue line in terms of y, this y equals x over 2, is going to be 2y equals x. So my right is 2y minus my left, which the square root of x equals y. So that means x equals y squared. So I'm taking 2y and subtracting y squared and integrating that entire shell area, the height times the circumference, that area I'm integrating with respect to y. So pulling the 2 pi out in front, just to make it a little easier, we'll go from 0 to 2, and then I'm going to FOIL 3 minus y times 2y minus y squared. So that will be 6y minus 3y squared minus 2y squared plus y cubed when FOILed out. And I can simplify this down. 2 pi from 0 to 2. I'll combine my negative 3y squared with my negative 2y squared. So I'll have 6y minus 5y squared plus y cubed, integrating that with respect to y. That's going to be 2 pi times 6y integrated will be 3y squared, integrating 5y squared will be 5y cubed over 3, and then integrating y cubed will be y to the 4th over 4, and I'm using my bounds for y, which go from 0 to 2. Not those x values of the coordinates, the y values of the coordinates. So solving this out, plugging in 2 for y, 3 times 2 squared, 3 times 4 is 12, minus 2 cubed is 8. 8 times 5 is 40, so that'll be 40 thirds, plus 2 to the 4th is 16. 16 over 4 is 4. So if I have 12 plus 4, that simplifies down to 16. So I have 2 pi times 16 minus 40 thirds. Now, finding that common denominator will be a common denominator of 3, which means multiplying 16 by 3 is going to give me 48. So I'll have 2 pi times 48 thirds minus 40 thirds, which simplifies down to 2 pi times 8 thirds, which overall does indeed give me 16 pi over 3. That was the answer we got when we used the disk method, and it's the same exact answer we got when using the shell method. There we have it, a great double check. Now just to reiterate one more time, when doing the shell method, we're integrating the area of that shell, which we find by doing the shell circumference times the shell height. The height is going to either be top minus bottom or right minus left, depending on what we're integrating with respect to, and that shell circumference is 2 pi times our radius r, where r is the distance from that line we're revolving around to our rectangle. So it's either going to be an x or y, or it's going to be x plus some constant, y plus some constant, or some constant minus x, or some constant minus y. Those are the different cases, and it all depends on where that line is in respect to where our function or where our region is bounded. So hopefully with this video, you got some really good examples and practice in. I definitely recommend practicing more, even if it's just setting up these integrals, because setting them up is half the battle. Integrating from there is just using your integration strategies and techniques. And as always, if you have any questions, please feel free to contact me and I'll help you out with any of these problems. But until the next video, good luck with your online learning.